Rachel asked me to do a homework problem. I'm just going to go ahead and start it, even though everybody's not in here yet. It said this is in your 7.1 homework number 4. We did these last time. It was that uniform distribution, and we said, remember, that we made that little box and did the length and width of the area. So the first one says the random number generator on a calculator randomly generates a number between 0 and 1. The random variable x follows a uniform probability, which means it's straight across. Part A, identify the graph of the uniform density function. So it says it goes from 0 to 1. So this last one does not go from 0 to 1. So we know that it's not going to be the last one. So these first two go from 0 to 1. Now the only difference is how tall it is. And we said we take all these little sections and put it over 1. So this goes all the way up to 1. So the number up here is going to be 1 over 1. So the first answer is going to be A. It goes out to 1, and then you take the 1 and put it over 1. Okay, so our first answer is going to be A. Now, question B says, what is the probability of getting between 0.44 and 0.61? So if I have 0.44 and I have 0.61, and I make me a little box, I need to know the area of that, which means I need to know the length and the width. We know that it's 1 tall, but we don't know how wide it is. So the way that you're going to get the width is you're going to subtract these two. So I already know that the height of it is 1, so this is part B. So we're going to do area equals length times width. We already know that it's 1 tall. And so to get the width, we're going to do 0.61 minus 0.44. What is that, y'all? 0.17. So my area is going to be the height, which is 1, times the length, which is 0.17, and I just subtracted those two. So for part B, your answer is going to be 1 times 0.17, which is going to be 0.17. And then for part C, there's your 1 and there's your 1. It says greater than 0.87. So if this was 0.87, we want greater than 0.87. So we know the height is 1, and we want the difference between 0.87 and 1. So we're going to do the same thing. We're going to subtract 1 minus 0.87. Oops, get my eraser. So if this is 0.87, the distance is going to be 1 minus 0.87, which is 13. So I'm going to do area equals length times width. So my length is 1, and my width is 0.13. So the area of that is going to be 0.13. Does that make sense?
Yes. Yep.
All right. So now 8.1 and 8.2 is still going to be doing the normal CDF and the inverse normal CDF, but it's going to be doing a little bit different. The last term is going to be changing. Okay? I'm not going to talk too much about it right now, but I just want to show you. In chapter 7, I'm going to kind of show all of it. This is chapter 7 versus chapter 8 stuff. In chapter 7, when we did normal CDF, we did where the shade begins, where the shade ends, the mean, and the standard deviation. In 8.1, we're going to be doing shade begins, shade ends, mean, and standard deviation over the square root of the sample size. And in 8.2, we're going to be doing shade begins, shade ends, the p, and the square root of p, 1 minus p over n. So all of the beginning stuff is going to be pretty much the same. The ending stuff is what's going to be different. So, and all of these, this is going to be the mean, and this is going to be the standard deviation, okay? Now, we're going to watch some videos in just a minute, and I know we usually don't watch videos, but it'll kind of explain what we're doing. This is if we have a single piece of data. This is if we're doing mean or group sample pieces of data, and this is if we're doing probability. But I'm going to show you a couple of videos, 2 different videos. That's why I wanted you to take a break so that you would kind of be awake. But these are the 3 different things. So we're still going to be doing normal CDF. You just have to be saying to yourself, what was I given? Was I given X, the mean and the standard deviation? Was I given X bar, which is the mean? And then how many, this kind of reminds me that I'm going to be doing the size of the group. Tells me that I'm going to be dividing by the square root of the size of the group. So what I'm going to be given is going to determine what I'm going to be using. So I'm going to pull up 2 little videos. It's going to kind of, Travis, let me see if I can get it to pull up real quick before I go to the videos. Until I can get it fixed, which will be this afternoon, let me show you if I can get it pulled up. To learn was not wanting to work. If I go to Ms. Cooper's lecture notes, when I was putting the notes out on YouTube, y'all, I called like 5 days of notes, 5-1 and 5-2, instead of, I changed the date, but I didn't change the section number. Let's see if I can get this to pull up and I'll show you. I'll go out there this afternoon and change it. He kept saying, all I see is 5-1 and 5-2. I didn't change the section number, I just changed the date. Come on.
That stuff can take a while.
There we go. Okay, so if you scroll down, okay, 5-1, 5-2, those are the videos that go with 5-1, 5-2. And then 5-2, 5-3, 5-4, 5-5, these are the videos that go with that, even though they're called 5-1, 5-2 right there. And then 5-5, 5-6, 6-1, these are the videos that go with that, even though I call them 5-1, 5-2. And then 6-1, 6-2, these are the videos that go with that. So that's another way that you can kind of see it as well. My bad. I'll fix that. All right, now I am going to pull up 2 little videos. And they do, y'all know how to do chapter 7, the plane inverse norm and the plane norm. This first video is going to show you the difference between 8.1 and 8.2. I'm going to come down here to videos. And they're listed out here for you to watch as well. And we're going to do 8.1 and 8.2. This is going to show us the difference between 8.1 and 8.2. Didn't bring any popcorn for you.
Sampling distributions. It's important that you understand this idea of sampling distributions. The big part of sampling distribution is the ING. Because the way you get a sampling distribution is by sampling, and 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 sampling. Let me explain. There are 2 sampling distributions that you're introduced to early, and there's a couple more we'll talk about later on, but this is the first one that we're going to talk about, are the sampling distribution for proportions and the sampling distribution for means. Let's talk about how we get those things. So imagine, let's talk about proportions first. Suppose that I told you, or we knew that 20% of the people were sexy and they knew it. So let's suppose 20% of the people are sexy and they know it, actually out there in the population. So that would be the parameter. The actual population, 20% of the people were sexy and they know it. So I say P equals 0.20, okay? P is the proportion of the population. But if I go out and take a sample of 100 people, do you think exactly 20 people will be sexy and they know it? Do you think that's going to happen? No. Because if I take this sample over here, maybe only 18 people are sexy and they know it. If I take another sample, a random sample again, maybe only 20, maybe 17 are. Then I take another sample, maybe 24 are. But most of those samples, close to about 20, will be sexy and they'll know it. So that number, 20 over 100, or 22 over 100, or 21 over 100, would be the proportion in my sample. A sample proportion is known as a p-hat. So if you can imagine this, me going out, I'll show you a little scale here, and we get about 20, 25, 30, 15, and 10%. I'm going to go out and I'm going to take a random sample of 100 people. So ready? Here's 100 people. Oh, in this sample, this random sample, 18 out of the 100, which is 18%, were sexy and they knew it. So right around 18, I'm going to put a little p-hat. And then I take another sample, and I find out in that sample, 22% were sexy and they knew it. So 22%, I put another p-hat. And then I go take another random sample of 100 people. And of those 100 people, 24 were sexy and they knew it. So 24%. And then the next sample I take, 27% were sexy and they knew it. And the next sample I take, 14% were sexy and they knew it. And I throw them all back in and I take another random sample of 100 people and I find, 16%, and another random sample. And I just take random samples and I keep getting a bunch of p-hats, which are my sample proportions. Okay? As opposed to P, which is the population, the truth. But if I go take a sample, it's most likely not going to be exactly the same proportion as the population. But notice that I take different samples have different proportions. Why? Because they're different. They're not the same people. So it's not a group of 100 people. So just because I take a sample and find 18% of something, of the sample has this quality, I don't say, well, I know for sure that the parameter is 18%. Because we know samples vary. And if you did an experiment in your class and you took like handfuls of beads and calculated the proportion that were green or something like that, notice if you do that and take many handfuls, you're not going to have the exact proportion of green all the time. And it's going to be a different handful. This thing that goes back and forth, these little p-hats, the way they vary, is called sampling variability. It's also known as sampling error, even though you didn't make a mistake. It's just the natural variability between statistics. Statistics are the numbers you calculate from a sample. So all of these p-hats are statistics. But notice, if I keep doing this over and over and take another sample, what shape do you notice? Most of my p-hats are pretty close to the true p. Most of my p-hats are pretty close to the true p. As a matter of fact, if I keep doing this infinitely, I end up getting something that looks like this. I think you've seen this before. Something that's not perfect. Maybe I bring it over here. Something that ends up being normalish, symmetric, centered at the true p. It's amazing. All of these p-hats, if I take a p-hat, another p-hat, another p-hat, many of them are really close to the true p. Some are a little bit away, some are both, but most of them are near there. And what ends up happening is you end up getting a sampling distribution. So this thing right here that I got from sampling and sampling and sampling and sampling and sampling is a sampling distribution. You get it from sampling and sampling over and over again. So this distribution, this histogram of all of these p-hats is a sampling distribution for proportions. It's a bunch of statistics, a bunch of p-hats. Piled. They're piled, and notice the pile is right around the true p. And what's even cooler about this, it can be derived mathematically, is that the standard deviation from this is actually given to you right on your formula sheet. Two things are given to you on your formula sheet. It says the mean of all the p-hats is simply the true p. So the mean of this model is 0.20, which is the true p of the population. And what also is given to you on your formula sheet for the AP test is that the standard deviation of all the p-hats is simply the square root of pq over n. So I can find the standard deviation of this thing by using my calculator. pq over n. Square root pq divided by, I already know this comes out to 0.04. For this p, 0.2, q, which is probability of failure, 0.8, these add up to 1, over n, 100. I find out that the standard deviation of my p-hats, in this case, is 0.04. So I have a normal model centered at p with a standard deviation of 0.04. P, I go up 0.04, 4%. So notice if I start drawing my lines, I go up another to 28. About 68% of my p-hats will be between 16% and 24%. About 95% of my p-hats will be between 28% and 12%. So the same thing happens. You have 68% within one standard deviation, which is 4% within 4%. You have 95% of the p-hats will be within two standard deviations. Kind of cool. The other sampling distribution is you have to imagine some population out there. Suppose that, what was I using for an example? Oh, suppose the average student texts. Suppose we know that the true mean, the number of texts a student sends during one of my class, during an AP class, is about 30, with a standard deviation, a population standard deviation of 10. So if I randomly took some students, and I found this, I randomly took 100 students and I calculated the average that they took during class. If we know the population average is 30 per class, the average student texts 30 times per class, and I grab all 100 students, are those 100 students going to have an exact average of 30 texts per day? No. Maybe there's a couple super texters in there that text like hundreds of times. They just text the whole class. You know who you are. You like that. You sit at your desk and you do the old lean back and then, okay? We know who you are. But maybe there's a few of those who brings the average up to, 35 or something in that group of 100. But you have to imagine what the sampling distribution looks like. It looks like this. I go out and I take, so here we go, 30. And I go out and I take a sample and I find that the average in this group is 30.5 or something. There's my X bar. The X bar is my sample mean. It's a statistic. So I go out and take a sample, I find about 30, a little over 30. I take another sample, there weren't that many texts, I found like 28, so let's just go up one and down one. And I just keep going up and I keep getting X bars. This sample had a ton of texters in it, people that text a lot. I took another sample, there weren't that many texters. But in most of my samples, the average number of texts per class is about 30. And it should be. And what ends up happening here again, is that most of these X bars are near the true mu. And that pile of X bars, they all pile up around the true mu and they end up being like this. Something like that, a whole bunch of X bars, normal-ish. Again, as long as the sample size is large enough or you know the underlying population is normal-ish. And we'll talk about that later. But the X bars all land near the true mu. And we know, given on our formula sheet tells us this, that the mean of all the X bars is just the true mean of the population. So all the X bars are centered around the true mean. And the standard deviation of all the X bars, the formula is given to you, is the population standard deviation divided by the square root of sample size. So suppose my sample's 100, then I can find the standard deviation of all these X bars, the standard deviation of all these X bars, is the population standard deviation of 10 with a square root 100, which is 10 over 10, which is 1. So 31, 32, 29, 28, and if I go up like this, I find that if I go up one standard deviation and down one standard deviation, 68% of my X bars, if I took sample and sample, remember I'm taking a sample, calculating an X bar, putting it here, sample, calculating an X bar, putting it there. This pile of X bars is a sampling distribution. I didn't get it from one sample, I got it from sampling and sampling and sampling. 68% within one standard deviation. 95 within two of those things, those standard deviations. 99.7 within three, about, approximately normal. So just remember what a sampling distribution. It's not the distribution of a sample, because the distribution of a sample is just a histogram. You take a sample and make a histogram. It's not the distribution of a population. Those are a bunch of individuals. It's this, taking a sample, calculating a statistic from that sample, and putting it over here in a little list. You can make sampling distributions from any attribute you calculate from a sample. You can make a sample sampling distributions of sample standard deviations or sample medians. The same thing, but what you're doing is you're calculating something from a sample, putting it down, taking a new sample, putting it down, taking a sample, grabbing the next bar, putting it down, taking another sample, grabbing the next bar, or taking a sample, calculating the p-hat, writing it down, taking another sample. It's a bunch of p-hats. It's a bunch of statistics taken from a bunch of samples. So if you imagine a pile of p-hats, that pile is a sampling distribution. It comes from sampling. Or if you can think of a pile of x bars, those x bars are sampling distribution. I can be crazy. I can, you know what? I'm going to go out and I'm going to make a new sampling distribution. I'm going to make a sampling distribution of sample medians. And I go and take a sample and I calculate the median and I write it down. And I go take another sample and I calculate the median and I write it down. And I have a pile of medians. Well, that would be a sampling distribution for sample medians. I got it from sampling. So don't confuse with the other thing. Just remember, a sampling distribution comes from sampling and sampling and sampling. It's a distribution of a bunch of statistics. The statistics are generally piled around the parameter, the truth in the population. Good luck.
That's kind of pepper. All right, let me show you one more, and this one's not as long.
What? Still searching YouTube for math help? Are the videos from 2006 really helping? Aren't you tired of finding videos that aren't get
Somewhere in the fields, a brave ecologist is studying
hear that?
wild rabbits. He plans to record the weights of every single rabbit. If he follows this plan, he will notice that most of the rabbits are close to the average and that there are some rabbits, but not many, that are much larger or much smaller than the average. The further from the average you get, the fewer animals there are. This particular bell-shaped curve is called a normal distribution. Sadly, he has to give up his experiment, for it will cost him a fortune in carrots to complete it. So, he changes the plan. Instead of measuring every rabbit in the whole group, he decides to measure rabbits in small groups, chosen at random from the whole group. He knows that each small group won't necessarily be perfectly representative of the whole group. So he measures many small groups and then compares the averages of each. He starts by weighing 5 rabbits at a time, and he finds that the distribution of the average is somewhat bell-shaped. Then, he increases the sample size by weighing 20 rabbits at a time, and then 100 rabbits at a time. Surprisingly, as the sample size increases, the spread decreases. The distributions of average weights becomes more and more normal. What our brave ecologist has just demonstrated is the central limit theorem. The averages of samples have approximately normal distributions. If the sample size increases, this distribution of averages becomes more normal and narrower. What if the population distribution is not normal to begin with? For example, the distribution of dragon wingspan is known to be bimodal. If an even braver ecologist were to study wild dragons and measure dragon wingspans, the distribution of the average wingspan would still be approximately normal. And again, the more dragons our brave ecologist could measure at a time, the closer the distribution of their average wingspans will be to a truly normal distribution. The distribution will also be narrower. So now we know that regardless of a true distribution, the central limit theorem shows that the average of values drawn from the distribution will always be approximately normal. Furthermore, the bigger the sample size, the narrower the distribution of average becomes. And the closer the mean of the sample gets to the true mean of the population. This is why sample size matters so much in any statistical analysis, whether it is a political poll or evaluation of a medical procedure. There is something very special about the normal distribution. Not only do many things we measure in biology follow a normal distribution, but it also crops up when we look at estimates of variables, even when the variables themselves don't have a normal distribution, as we saw with dragon wings. Because of this, we can use the normal distribution to test ideas about the world even when the underlying variables don't follow a normal distribution. My name is Buthikrit Bhattacharya. This video was created by Shui Cho and brought to you by Crinchcast.
Alright, so this is all to show you that what we were dealing with in Chapter 7 was like individual data. You know, I gave you a test score, or I gave you a month of pregnancy, or a day of pregnancy. I gave you like an individual data. In 8.1 and 8.2, we're not dealing with individual data, we're dealing with samples of data, but we're doing the same thing, okay? We're still going to be doing inverse norm, we're still going to be doing norm, but we're gathering data differently. So, and I'm going to start with 8.1, and we're going to talk about, you're still going to be doing the normal distribution, you're still going to be doing where does it shade starts and where does it shade end and what is your mean. The only difference is your standard deviation is going to be different. And the way that I think about this one, and it's not mathematically right, but for what we did in Chapter 7 was individual data. Like if you're taking a picture of an individual, it is what it is. Your spread is your spread. If you're fat, you look fat. If you're skinny, you look skinny. You're an individual, it is what it is. Your spread, it is what it is. It's individual data. This is like group data. You're doing groups of data, okay? So over July 4th, some of y'all had gatherings and you put people in pictures. You were doing sampling, okay? Now, you don't think about it, but when I'm like paparazzi. When I went on the cruise, I was taking pictures of everybody. And if you put a lot of people in a group, think about what that picture looks like. A normal distribution. You always say, okay, y'all get together, put the big people and tall people back here, put the short people over here. So when you have a bunch of people, it kind of looks like a normal distribution. So in my brain, when I'm doing grouped data, this is sample size, when I'm doing group data, I love taking pictures with a lot of people. The more the merrier. The skinnier I look, the photographer always says, turn to the side and suck in, okay? Your standard deviation, your spread changes by the size of the group. So if it's an individual data, it is what it is. If it's group data, you're doing sampling, you're doing a group picture, you're not, like here, if you're a size 16, you're a size 16. Here, you don't look like a size 16 anymore. You go from this big to this big. So you're changing according to how many people are in the picture. Everything else is the same. Where it shades begin, shade ends, the mean. So in all of these problems, the mean is the mean is the mean. So when I say, did the mean change? No, the mean didn't change. The mean is the mean, whether there's one person or whether there's 100 people. The mean is still going to be the middle of the picture. But the size, suck it in, there's more people in the picture. So when I say you have a group of 50, you're going to take your original size and divide it by the square root of 50. That's what we're talking about now. And then I'll talk about 8.2 when we go into 8.2. So we're just putting more sampling, more groups in there. Now, and I'm only going to talk about the 8.1 right now. The mean is the mean. The mean is the mean. Standard deviation, if you're by yourself, it is what it is. If you fat, you fat. If you skinny, you skinny. It is what it is. Here, if you're fat, you're going to divide by the square root of the size of the group. We're going to make you look skinnier because you've got bigger groups. You've got more people. So this is going to be that individual, and this is going to be the group. So this is going to be mean equals mean. Mean equals mean. This is standard deviation equals standard deviation. Here, your standard deviation is going to be divided by the size of the group. Now, a normal size group, we don't want to do groups of 5 or groups of 7. We like our group size, our sample size, to be at least 30.